lecture will be on mechanisms of device operation and potential architectures for efficient enhancement. And Sean, as we heard yesterday, is from the University of Denver in the US. Sean.
Very good. Thank you, Alina. Thanks everybody for sticking around for rounds number 3 and 4. So one of the benefits of a workshop style or more free workshop style is that we can change topics. And I thought I would insert a few slides relevant to Ricardo's talk that we just heard about. Because our group in Colorado has worked on zinc oxide over the last 5 years. So I just put in a few extra slides that are not relevant to excitons per se, but about interesting device architectures. So I've showed you pictures of these mixtures of molecules, of donors and acceptors that would be used to generate the free charges. And a common picture that you see that people will show are these sort of very straight pathways where we intercalate the donor and acceptor, but in a very ordered fashion, so that the exciton would dissociate at the interface, and positive charge would go this way, electron charge would go that way, and then very clear highways to move along. So we wanted to go by making something like this, and looked in the literature and saw that actually zinc oxide, this nanomaterial, can make very nice nanofiber structures. So there's a paper in 2001 by Bassier where he grows zinc oxide nanofibers in a method very similar to Ricardo described. You start with a glass substrate, you deposit a nucleation layer or a seed layer that is deposited from zinc acetate as a precursor. It's very simple. You dissolve it in an alcohol, spin coat a thin layer, and then put it on the hot plate at 300 degrees centigrade and convert it into nanocrystalline zinc oxide. You then take the seed layer and put it into a growth bath. And the growth bath can be more zinc acetate, or it can be another growth material, zinc nitrate, which tends to work quite well. And depending on the pH of the solution and the concentration, you can grow nanofibers of whatever length you like. Also how long you leave it in the growth bath. And these are in principle single crystalline. They have different crystal facets. And if indeed they are single crystalline, the mobility of the carrier should be extremely high, should be something like 100 centimeters squared per volt second, which is more akin to a crystalline semiconductor and much higher than an organic material. So this is one of the samples that we grew. And then we need to make a complete device out of this. So how do we do that? Well, just to follow the steps, we again start with ITO, this transparent conductor. There's our zinc acetate as a seed layer. We thermally anneal it to get the zinc oxide, to get pure zinc oxide. Then we grow the fibers using the zinc nitrate. And then we just spin coat a polymer solution and hope that it infiltrates or goes into the nanowires. And then deposit a silver top layer. And ideally, we would have just a little bit of polymer on top here that's protecting the zinc oxide wires from the silver electrode, since the silver electrode is the positive electrode, and down here becomes the negative electrode. So here's a cross-sectional SEM, and you see that the picture and the cartoon are certainly not quite the same, that the fibers are much more disorganized, the spacing is not uniform, that's why I asked that question. And we certainly do not have perfect filling. There's some pretty large gaps in here between the polymer and the zinc oxide. Nonetheless, we proceeded to make a device to forge ahead, and here's some of the JV curves of this device. There's another cross-section of a slightly different version of that device. You can again see very large voids in there. So in the end, the device did not work quite as nicely as we had hoped. We got about 0.5% efficiency out of it. The currents were pretty low, voltage is pretty low. But nonetheless, it worked. And actually, we learned something very valuable from these devices, which is that these devices are very stable in air. Because we're using a silver top electrode, there's no metal such as a calcium that could degrade. And so this device showed us that when you put silver on top, you can have a very stable device. So we learned quite a bit. Another interesting thing is as you turn up the light intensity, so this is light intensity, this is efficiency, here's open circuit voltage. So we explained before that as you turn up light intensity, that in principle, any solar cell should get more efficient. But in reality, for organic photovoltaic cells, they tend to become more efficient up until about 100 milliwatts per centimeter squared. That's about 1 sun. And then they tend to come back down for various loss mechanisms, mainly because of the loss in the fill factor, because there's just too much charge in the device. Well, this device with the nanofibers actually continues to improve at higher light intensities. So somehow these pathways, the zinc oxide pathways, do efficiently move the charge out of the device, even at very high intensity. So we continued with this work a little bit more, and we were able to get a little better filling of the polymer into the zinc oxide, but never really got a substantial efficiency that got us too excited. So we sort of put that project aside, but I think there's still a lot of good science to be done. And even from a device efficiency standpoint, there's probably some tricks that can be done. Okay, so I mentioned this inverted device, and we talked about the band structure where we put a zinc oxide here in the ITO. So what we can do is just remove the nanofibers altogether and just use the seed layer as an injection layer in the device, and that's what we did. So we have ITO, we have the seed layer, and then now we can put the bulk heterojunction active layer, that's the blend of the polymer and the fullerene, and then a silver top electrode. So this is our inverted device. And we sort of, again, learned that trick by going through the nanofibers and then saying, oh, let's remove the nanofibers and just put the blend on top. Just to give you an idea of that seed layer, the zinc oxide seed layer, it is nanocrystalline. So in the AFM, you can see there are these little spheres here, about 25 nanometers in diameter. So when you anneal the zinc acetate, the zinc coalesces and oxidizes, and you get these little nanospheres. So anyhow, at the time we had a 2.6% efficient inverted device, which was also a world record for at least a couple months. But now they're inverted devices above 5-6%. Okay, so back to the original sort of sequence of topics. And I'm going to continue with this issue about morphology and mixing of the molecules and how that affects the charge transport in the devices. So the assumption here is that these materials, all the organic materials, are very disordered, and we do not have the perfect band theory charge transport, but we have hopping transport. And one of the consequences of that is that the intermolecular communication must be poor. We have poor coupling between molecules. So we wanted to test that by doing some high pressure measurements. So we were working with the groups of Paul Rudin and Dan Frisbee at the University of Minnesota. And they have a high pressure hydrostatic cell where we can put a device in and turn up the pressure up to something about a gigapascal, all right, so 1,000 million Pascal. And what we did was make transistors. So we made thin film transistors from the material P3HT, so it's a neat material, it's unblended. And we wanted to see what would happen to the carrier mobility, or the velocity, as a function of pressure. Well, first we ran into a bit of complication because when we just measured the current as a function of pressure, we noticed it went up and then it went back down. So that confused us a little bit. But then we realized that the threshold voltage, for a transistor, there's a threshold voltage that is essentially the turn-on voltage, that actually went down with pressure. Well, when you can deconvolute these two and extract out the carrier mobility, you find that the carrier mobility is basically linear with pressure. So indeed, as you squeeze the molecules together under higher pressure, the mobility goes up. Now, the surprising thing is that we expected a nonlinear, at least I expected a nonlinear function here, right? So molecular orbitals are exponential functions. They are solutions to the spherical hydrogen equation, right? So Bessel type functions. So you'd expect something like this. Well, we see a linear function here. So what that tells us is that the molecules are really decoupled from each other, and they're far away from the limit of an exponential turn-on. Presumably, if we go out to much higher pressures, maybe something like 10 to the 9th Pascal, this will finally start to turn up exponential. So I hope one of my dreams in the future is to get a new high pressure cell, and the new ones now go up another factor of 10, and we need to redo this experiment. But anyhow, what we learned is the materials are in fact very disordered. Okay, we've seen this slide before. What's the impact of disorder? Well, that means the mobility goes as the exponent of the minus of the disorder sigma, and that's a measure of the disorder, and the square root of the electric field. So whatever model we come up with, it should sort of fit this functional description. Okay. So one of the big issues in the field, and it's true for any semiconductor, is the defect density in the material. And the presumption is that we may have a Gaussian distribution of energies, but on top of that are some defects that may sit much lower in the band that can trap charges. So there's a number of groups now working on this area trying to discover what is the nature of those defects. So we've started to do this as well, and what we're doing is a computational simulation, a Monte Carlo simulation, to investigate these defects. So what we do is create a lattice, a Monte Carlo lattice, which is something like 6,000 sites long, and then is something like 50 by 50, or we can now go larger, we can go 200 by 200 sites on the side. And this is a simulation of a real material that we would do an experiment on. And the type of experiment we're doing is called time of flight, or TOF. And in this experiment, we create charges on one side of the material, we hit it with a large electric field, and then we follow the currents as the charges migrate across the material. So in the model, we are implementing this distribution of energies, and we get to do that manually. We get to decide all the energies. So for every site in the lattice, there's the lattice here, we assign an energy that comes from a distribution, and then we have to compute the probability for hopping between sites. So that probability, I showed you before, I showed you before the Miller-Abrahams formula for the probability. Well, there's another formalism that we could use, which is Marcus theory. So Marcus theory is in general a description of charge transfer in molecular species, and under certain conditions, one can use it for semiconductor work as well. So we're doing that here, and under the Marcus theory description, you again have a nu naught, which is sort of an intrinsic hopping rate that has to do with how fast the molecules are, or the attempt frequency between the molecules. And then an exponent that goes as the energy difference, delta, between two sites. So delta is Ej minus Ei, that's the energy difference. And then there's an energy term from the electric field. So you apply an electric field, and that creates an extra term in the energy. Most importantly is this lambda. So in Marcus theory, is driven by the reorganization energy. That is, when you put a charge on a molecule, all the bond lengths will change a little bit, the electronic cloud will change, and the difference in energy between the neutral and the charge state has something to do with this reorganization energy lambda. So that's the driving factor here. So we get to control all that in the molecule and in the lattice. So what we do is start with a Gaussian distribution. So here's our Gaussian distribution. Sigma is an input factor. It has to do with the width of the Gaussian. So what we do is we have a transport band, which we call the main transport band, for hopping down the lattice. And there's an average energy there, E naught. Now, at present, there's no defects in there. There's just a distribution of energies. So what we do is now come in with what we call a trap band. So these are traps that are in the material. They come from impurities or kinks or bends in the polymer, some sort of mechanical defect. So we insert those in, and now you can see that a charge could potentially fall into a deep level trap and be stuck there for a long period of time. And presumably the density of these traps is a lot lower than in the main band. Okay, so now we can carry out a simulation. We populate the lattice with some charges just on one side. We turn up the electric field, and then we can measure their velocity as a function of time. Well, in this case, we measure their average velocity. So we would expect, or we hope that we get this pole-Frankel dependence, where mobility goes as the exponent of the square root of the electric field. So if we plot electric field versus mobility, we hope for, square root of electric field versus the log of the mobility, we hope for a straight line. So you see it's not perfectly straight, but under a small range of fields it is. And again, I told you that under the Gaussian disorder model, where there's no correlation, you don't get a perfect fit, and we see this here as well. So we have not put any correlations in the energy, so it's not a perfect straight line, but it's pretty close. And in reality, when you go to measure a real material, you also don't get a straight line, because oftentimes those correlations aren't quite perfect, or they're not homogeneous. So we think that this is at least a test that our model is fairly reasonable. And there were no traps in this model, we just had the main band. Okay, the next issue is this lambda, this reorganization energy. And the question is, how does that affect the mobility or the velocity? So we can plot out the reorganization energy, or the mobility as a function of reorganization energy. And what you see is that when you first turn on the lambda, that the mobility actually goes up, reaches a maximum, and comes down. And the placement of the maximum depends on the electric field. So for larger electric field, the maximum is at a higher reorganization energy. So this confused us at first as well. Most of the discussions in the field always say, well, you want the lowest possible reorganization energy. And that's true if there's no field. If you just have two molecules, one has a charge, there's no electric field, you would prefer lambda to be 0, and that would give you the highest rate of charge transfer. But when there's a field term, and the field term is that F that's inside the delta, now this top of the exponent goes to 0 at a non-zero lambda, right? So for reorganization energy of 0.07, actually there's the best mobility, or sorry, for a field strength of 9 to the 5th, the best mobility is at a lambda of 0.07, and so on. So this is a bit of a surprise, but it means that you actually don't want 0 reorganization energy, but you want something non-zero. So some lessons to be learned there. Okay, so let's start adding some traps to the simulation. So we've got that main band. Now we're going to start adding a little bit of traps. And sorry, this is no traps. Okay, let me back up. This is no traps, but what we can do is monitor the current as a function of time and measure the transient of the signal in the material. And this is what we would actually measure in the time of flight experiment. So let me go to a log plot here. So as you turn up the voltage, the carriers make it across the film faster, and then what you see is a decay as the carriers start to exit the device. So for 100 volts, this exiting point is much earlier, so that's at about 100 microseconds. And then the lower voltages, this time goes out to longer times, okay? All right, so that makes sense. Okay, now let's add some traps. So in this case, we have a reorganization energy of ½ volt, which is roughly what it should be. And the main band energy is at minus 5.2 electron volts, and the trap energy is at minus 4.5. So there's a 0.7 eV difference between the trap and the main band. So if you have no traps, this is the transient. You get a straight line here as the carriers move across the film. You get a constant current. And then they start to leave the device, and so you start to lose current. So the red now is with traps. So we're going to add traps. We're going to add 2% traps. That's 2% by number density of traps. So what you see, first of all, is this part is no longer flat, that there's some decay. And what this is essentially thermalization. Right? You initially populate the carriers across the whole lattice, and then over time, they'll tend to fall into the lower energy states, into the traps. And so you see some thermalization here. And then they start to exit the device, right? So there's the curve. Now, if you look on a log plot, you see that the tail actually extends out many orders of magnitude in the trapped case. So these here are carriers that are deeply trapped that are slowly moving out of the device. Okay? So a big difference in these curves, particularly in the log plot. So what's the reality? Well, if we carry out the simulation or carry out the experiment, so in this case, the red curve is the experiment, so time of flight signal from a blend of P3HT PCM, and then try to fit it with our model. Actually, we can get a very good fit if we put in this case, a trap density of 5%. And the trap, there's a width on the trap as well as 0.3 electron volts. So there's a sigma on the main band and a sigma on the trap. In this case, the trap width is 0.3. So anyhow, we can get very good fits. We could probably play with those parameters a little bit more and get slightly different parameters to fit that curve. But the bottom line is that the material does have traps in it, and it does affect the shape of the transients. So we're going to continue with this in our laboratory and try to investigate the effect of correlations and see if we can actually change the trap density in the material by doing some different processing steps. Okay? So organic materials have some traps in them, and they definitely control some of the time dynamics. Okay, so the next topic is how to control the excitons. We said the excitons are the mediator for the energy control or energy creation in the device. So what are we going to do to control their energy and their location in the molecule? Right? They control all the physics. So this basically goes into, in the end, into a bit of organic chemistry. But first, let's start with some theoretical calculations. The question is, what band gap do we want in order to harvest the solar energy efficiently? So if you look at the black curve here, on the y-axis is photon flux coming from the sun. So that's photons per meter squared per second per micron, right? So it looks something like this. Here's an absorption band coming from, I don't know, probably water or something. The blue curve is the absorption of P3HT. And you see it doesn't get very much, of the spectrum. It has a band gap of about 1.9, something like 700 nanometers. And so we're missing all this in the red and infrared. So we'd like to move the green curve further to the red. And the question is, what is the optimal band gap? We know that as we decrease the band gap, that is, go to higher wavelength, we get more photons. We can see that here. So here's the band gap. Here is the current density, or essentially, if you absorb all the photons, turn them into electrons, what would the current density be? So as you decrease the band gap, you get more and more photons. And there's about 70 milliamps per centimeter squared available in the sun's spectrum. So on a bright day, if you collected all the photons, it'd be something like 70 milliamps per centimeter squared. And I told you for P3HT, we usually get about 10. So it's only 1/7 of the total available photons. So the current goes up, but we also learned that as you increase or decrease the band gap, the voltage has to go down. So that's the trade-off, right? And so the total power would be the current times the voltage, so there must be some maximum. So you can plot out the efficiency as a function of band gap, and you see that the maximum is about 1.4 eV and about 31 to 32%. Right? So this is called the Shockley-Poiseuille limit for a single junction solar cell. That is the best one we can do. So clearly we want to drive a little bit to the infrared towards 880 or 900 nanometers, but not too far, unless we're making a tandem device. If we're making a tandem device, then the optimum band gaps are actually 1.1 to 1.9 eV for the two different junctions. And so here we actually want a very low band gap if we want to do a tandem device. So we need some molecular design principles that can push towards the infrared, right? And so how do we change the structure of that P3HT to do that? So this now gets into a bit of organic chemistry. And we can come up with a number of different structure property relationships that dictate what is the band gap of a conjugated polymer. So one of the main theorists in the field is Jean-Luc Bréda. He's now at Georgia Tech, and back in the 80s he wrote a lot about the theory of these materials. He still does a lot of theory, but in particular he wrote about how to change the band gap of a material. So the band gap, e.g., of a conjugated material is controlled by a whole bunch of factors. Right? We've got E delta R, this is the bond length alternation in the material. E phi, which is the interring planarity, I'll describe these in more detail. E res, this is the resonance of the electrons in the material. E sub, which is substituents, those are the side groups of the material. And E interaction, there's the interaction between different polymers. So let's just go through these briefly. So what is the bond length alternation? Well, if you have a thiophene material, then normally you would have an aromatic structure, where you've got a single bond, double bond, single bond, double bond, single bond, right? Now that alternation is, by definition, what you need for a conjugated material, for pi electron conjugation, single, double, single, double, single, double. But if the bond length difference is very much, then the band gap goes up. And if you plot the band gap versus delta R being the difference between the single bond and the double bond, then you see for a large delta R, this large negative, then you get a large band gap. And somewhere around 0.05 difference is the minimum band gap in the structure. On the other side is called a kinoidal structure, where instead of single, double, you have double, single, double, single. You just reverse the bonds. And if you went completely the other direction, this would go back up, and you again have higher band gap. So somewhere in the middle, where those bond lengths would be roughly the same, you would have almost no band gap, meaning a metallic material. So in general, we sit over here with materials, and we want to push more towards kinoidal. We want to shorten this bond and lengthen that bond. Okay? So that's one of the main design principles. Another one is interring planarity. So you have two conjugated molecules, two thiophenes, or these could be benzenes, And ideally, you want them lined up parallel, right? You twist them on a plane, as you have some torsion angle, then the band gap goes up. But you would prefer them to be parallel. Okay, so resonance, aromatic resonance. So this is now a competition between electrons in the monomer species, like the benzene, or a thiophene, or a pyrrole, or this isothianapthene stuff, which I'll talk about in a second. So there's some resonant energy for that monomer. And for instance, for benzene, that resonant energy is 0.065 electron volts. When you then polymerize the material, take the polymer, polymerize it, now there's a competition between electrons staying in the monomer versus delocalizing down the backbone. And you would prefer them, of course, to delocalize. That would reduce the band gap and give you better conductivity. But if you have a high resonant energy per electron in the monomer, that's not going to happen. So as you decrease this resonant energy, the band gap goes down because the delocalization is better. So that's another principle we have. And already we know that thiophene has a lower band gap than benzene, and we tend to use those thiophenes as a good material. Another effect is substituents. So you can put a side group on the material, right? You can put an electron donating group, electron accepting group, and that'll affect particularly the position of the HOMO and the LUMO, but also the band gap can be affected a little bit. And finally, this interaction stuff. So if you have two chains of polymers and they're sitting right on top of each other, there'll be a little bit of sharing of pi electrons, and then the band gap will change a little bit. Okay? But these are somewhat minor effects to all the ones above. So one of the first low band gap polymers that was made was this isothianapthene, or a polymer version, polyisothianapthene. And this was made by Fred Moodle and Al Eger's group in Santa Barbara back in '85. And what they did was take the thiophene structure and just stick a benzene right on top of it. Okay. Now we said we wanted this bond length to be more like a double bond. And you can see if you have the benzene there, that forces that bond to be somewhat shorter, to be a double bond. So this drives it more towards the quinonal structure, and the band gap becomes much lower. It went from 2 eV down to 1.1 eV. So this material was a little bit hard to work with. It wasn't very processable. So the chemists decided that they could use the structure, but put it into a more complicated polymer. So about 10 years ago, we were playing with this material, and we had some copolymers that were synthesized in Belgium by the group of Dirk van den Hoogen. And what they did was to take that isothianapthene structure, this guy here, and then co-polymerize it with the normal thiophene. And this made it more processable, the chemistry was good, the materials were better purity, so we could make some kind of devices out of this. And depending on the side groups that were on here, here's some chlorines, here's some C12H25s, here's some sulfonated groups. You could change the band gap a little bit. So here's a 2 eV band gap with material, 1.4 eV, 1.6, 1.3. That one we couldn't figure out because it was so impure and so highly doped we couldn't measure it. But we had a range of band gaps to play with. And if you look at the absorption of the materials, so you can see the change in absorption with band gap. And one of the lowest materials was the P3. Just go back. So P3 is that guy, it was 1.4. And that had a reasonably low band gap and a nice absorption feature that we liked. So we made some devices out of this, and well, they weren't the greatest devices in the world. We got efficiency something like 0.2%. So the materials were a little bit disordered, and we weren't very good at processing at the time. But nonetheless, we showed some collection of charges down around 800 nanometers. So these are some of the first low band gap organic solar cells. Okay, so the field has progressed a lot in the last 10 years, and there's many more different molecules that have been developed. So one of the early ones after our work was this material that came out of the Netherlands, out of Eindhoven. And this material uses a little bit different concept. It's called a push-pull polymer. And what it does is it has moieties or monomers in the backbone that have different amounts of electron withdrawing or electron donating character. In this case, the center group here is an electron donator, and these guys on the sides are electron acceptors. So that tends to shuttle charge out this way, and the net effect is to even out the bond length alternation in the material. So that delta R gets smaller and the band gap gets lower. And this is one of the prime design motifs we have now for all of our materials. So this guy had a band gap of about 1.7. And they were able to make some okay devices, got efficiencies. This was 0.87 efficient device, or close to 1% device. So it was not a great world record, but it showed that this design principle worked. So people use that now to move on to much more sophisticated materials. I'll just show a couple quickly. So Ole Ingenes in Sweden is making material. His group is making materials based on polyfluorine. That's the structure here. This structure, which we saw before, is a benzodiathiazole, BDT. This shows up quite frequently as well. Another material was, again, the polyfluorine. Instead of a benzodiathiazole, you could add another group over here, make a much bigger electron donating structure, and in some cases get band gaps down to 1.2 electron volts. So don't bother memorizing these structures, I'm just going to flip through. Another more recent one is came out of the Santa Barbara group. And again, you see this benzodiathiazole, the BDT structure it's called, and then another just pi conjugated system. So this is the donor, this is the acceptor, and you get this charge transfer inside the molecule. And in this case, you get a band gap almost optimal, almost 1.4 electron volts. So what they actually have done with this material is also make a tandem device. So they use this as the low band gap side of the device, combine it with a high band gap material, and get absorption across the visible spectrum between the two materials. But I'll talk about that in a bit some more. And then even more recently, there's a group at Chicago, Looping U's group, who is synthesizing, again, polymers. I know it's a little hard to see, but there's a modi called DPP, dipyrrole, which is a very good also electron acceptor. And then we've got another aromatic system here. So this now they're blending not with C60 but with C70. So this is a elongated version of C60, and this has a little lower band gap as well, a little higher light absorption. So this set of materials now is the highest efficiency set of materials that's in the literature that we can read about. So the 8% and 9% devices, we can only guess at the structure because it's from these companies and it's not published. So this one, we know the structure, they published the processing, and depending on what solvents you use, here they're using dichlorobenzene and chlorobenzene and diiodooctane, you can get efficiencies up to 7.4%. So this is one of the best low band gap systems we have. Okay, so I don't want to focus fully on polymers. I said that people are also working on small molecule systems, and there are ways to change those band gaps as well. I'll just give you an example. So this is an oligomer. So we have a thiophene that is just polymerized into a very short chain. So N here is between 1 and 5, so between 1 and 5 thiophenes. And then on the end we have some cyano groups that are very good electron withdrawing agents. So that reduces the band gap of the system, and depending on the number of thiophenes N, the band gap gets shifted to lower and lower levels, right? So this is just the electron in a box model. Make the box bigger, the band gap goes down, the energy goes down, shift to higher wavelengths. So anyhow, here are some pictures of HOMO and LUMO levels, and those all get changed a little bit. See that the HOMO level tends to change a lot more than the LUMO level in this particular system. So highest efficiencies of these materials are about 5%, but a good example of controlling the band gap. Okay, so I want to finish up this section and talk about computational design. How do we predict what this band gap is going to be? So we can go to density functional theory, and if we choose an appropriate level of calculation, an appropriate functional, and a common one is called B3-lip, Becky 3-lip. And the basis function, for instance, could be 631 G star. This is a fairly detailed level of calculation. We can put in the structure into the computer and then pop out what the oscillation strength should be at a given wavelength. So this structure here is a benzene ring and 4 thiophenes. So we'll call it a phenyl attached to 4 thiophenes, PHDH4. And if you do the calculation with the DFT, you get a peak absorption here at 475 nanometers. So now let's take the same structure, a phenyl. Now we have 3 thiophenes, but let's add a little bit of the low band gap structure. My laser pointer just died. It's all right. So we've got a little bit of the low band gap structure here. We put a benzene ring onto the thiophene, and now we get a big shift in the band gap. So now the peaks have gone out to 600 nanometers. And then we move that position around a little bit. Instead of having it in the end, we have it more towards the center. And now it gets shifted out to 700. So you can see it's not only just the structure, but where along the polymer this particular structure is. Okay. We can keep going. So now we'll put that low band gap structure on positions 3 and 4. And by the way, the low band gap structure is called a thionylpyrazine, or a TP. So we've got a phenyl thiophene 2 TP2, and now we push it out to 750. And then if we do all 4, thank you. Now we make them all 4 TPs. Now we go out to 850. Okay. So that's what theory predicts. And the question is, how good can we get with these things? Let's look at work. Okay. Yeah. Let me skip that because that's more of the same. So one thing we want to see is when we change the structure, where are the excitons located on the molecule? Where are the excitations? So we can take the original structure. We can see where the HOMO and LUMO levels are. We can visualize those, right? We can also see something called the transition density. That is, as you excite the molecule, you pop an electron from the HOMO up to the LUMO, where are the transition dipoles changing the most? And you can see here, if we have this low band gap moiety over here, and this one tends to be an electron withdrawer, it just sucks all the transition density to that end of the molecule. So this is where all the exciton action is happening. And likewise, you can plot the charge density difference. So as you excite the electron from the HOMO to the LUMO, there's a change in the charge density across the molecule. So the different colors here, red and blue, would correspond to either a positive or negative change in the charge density. So blue is negative, and you can see again all of this charge density is sucked to the end. So we get an idea of where the excitons are. And I'm just going to finish up this section with one more plot. So one of the important things is when we start assembling these molecules, right, we can put different monomers in, we can put different arms on the molecule. We want to know how the exciton can delocalize across the structure. So one of the set of materials that we've been looking at is called a dendrimer, where we have a core group, in this case a benzene, and then we have arms, in this case which are made of thiophenes. And we can control the number of those arms and the length and the position. But we'd like to know if we excite one of the arms, we come in with a photon, what is the chance that that excitation will be delocalized across the molecule? So one way of looking at that is by plotting out this correlated electron-hole pair diagram. So what this is we can plot for the spatial extent of the molecule, and the molecule we can say has a core group, in this case there's a core group here, and then has 2 arms. Here's 1 arm and 2 arms. We can say, well, if we put an exciton on one of these groups, what's the chance that it shows up on a different group, right? So we're just plotting the correlation between these 2 directions. And we can do that for different molecular structures. And in this case, what we did is we have the core molecule, and we have the ortho geometry, where they're side by side, right? And then the meta geometry, where they're 1 bond away, and then the para, where they're in line. And actually, we see very distinct differences in the correlated electron-hole diagrams. So let me start with the meta. So in the meta case, if you see the difference between 1 and 2, it's basically blank. Meaning, if you put an exciton on one arm, there's essentially no correlation between the second arm. And that means there's no quantum coherence between this arm and this arm, because for the exciton to transfer, it's a coherent process. But if you look in the ortho case, if you look at 1, 2, there's a little bit of material there. Actually, go to the laser pointer. Okay, let's try again. There's a little bit of correlation here, a little bit of correlation there, meaning that there is some communication between the arms. And actually, we would expect that because if you go around the ring here, you have a more pi conjugated system if these 2 bonds are adjacent to each other. This would correspond to the single double, single double, single double alternating bond structure, which we need for a conjugated material. So bonding in the ortho position is more conjugated, and the meta position is essentially unconjugated. It's like this arm and this arm do not even communicate with each other. And then if you put them in a line for the para position, then you have a really nicely conjugated system. And now there's lots of correlation off axis. There's 1, 2 is very strong, 2, 1 is very strong. And you see that the core itself is well correlated with both 1s and 2. The core 1, 2 plots are 1 and 2. So using now the density functional theory, we can know what's happening with the excitons in the system. And in fact, we can get a very good fit to experiment in theory. So this is essentially for a molecule very similar to this. Here is the absorption and the emission. And then if you just go to the theory, you can actually get almost exact fit for that simple molecular case. Okay. All right. I think that's probably good for right now for part 1. So that's all I had to say about excitons. And I think we can wrap it up there and take a quick break.
We have a lot of time for discussions, questions to show.
I'm afraid I pummeled you guys pretty good. So.
Okay, let's have coffee then.
Yeah.
Another coffee.
Yes.
And,